different distribution, right? Because you're dealing with different data, you have different statistic, and that statistic has different sampling distribution, right? The reason we have t-test because that t-test statistic follow a t-distribution, okay? And the test related to categorical data often is called chi-square test. So a lot of chi-square tests. Of course, there are other kind of tests, right? But a lot of tests that test statistic has a chi-square distribution, so it's called chi-square test. But anyway, let's look at this first situation, right? First type of test. It's called goodness of fit test. Usually, this test is used for examining distribution, right? Whether data is normally distributed or not, or whether data is uniformly distributed or not. Of course, in our class, we're not going to talk about normal distribution. Normal distribution requires a little bit testing normality. That Shapiro-Wilks text that requires something more, right? We're going to look at something that sometimes people also use that, right? Instead of normality tests if they don't have a software to do it, okay? So let's look at it. This is a goodness of fit test, okay? And I'm going to use this example to explain it. So suppose you're examining a color distribution of candy, right? It was start with M and M, and I keep changing it. Now it's A and A, right? But it's candy, right? With colors. So the manufacturer has this kind of color distribution based on customers' preference. They do survey, right? So end up they get this distribution. They decide to manufacture their candy with 30% red, 20% green, and 50% yellow. But if the company says so and you don't believe that because you've been eating this candy, you found that the color distribution doesn't look like that, right? So maybe somebody did something or that there's a bad quality control in there. So you don't believe that. So what you want to do is take a sample and try to check the distribution of a sample to see whether it's still, supporting that 30, 20, 50 distribution. So what I did is I took a random sample, 200 of them. To 200 of this candy, and then find out that 56 are red, 52 are green, 92 are yellow. Right, this is just from one sample. If I take another sample, it may be different. But when you do a study, you only have allowed to get one time, right? That you're going to maximize the information you can get from it. So this is what you observed. So we call this observed frequency, right? And how do we deal with this problem to check whether the color distribution for this candy is 30, 20, 50%? Well, goodness of fit test is one option to do that. So this is a chi-square goodness of fit test. Anytime you do hypothesis testing, remember the first thing you have is stating hypothesis, okay? Now, the way I state these hypotheses look kind of awkward, or some of you may not like it, okay? But I'm using this cap F to denote the true distribution. The actual, right now, the color distribution, right, for those candies produced by the manufacturer. And F star stands for a specific distribution that you try to match, right? The companies say that I have 30, 20, 50%. So that's what we try to examine. That's this F star. Okay? So this is a theoretical distribution, and this is actually what you observe. And this is the actual distribution for the population of candies, right, in terms of colors. And what's a null hypothesis then, in this case? Null hypothesis will be the actual distribution of candy, right? It's no different from what you stated, right? 30, 20, 50, that's theoretical distribution. That's specific distribution. That's null. So no different. Remember I said null hypothesis, no different. So you're checking distribution. Your distribution is no different from what is specified there, 30, 20, 50, right? And the alternative will be what? It's different. So this population of candies, the color distribution is different from that, whatever we specified, 30, 20, 50. Does it make sense? Okay? So null hypothesis, again, hypothesis no difference, right? Remember, null hypothesis is always hypothesis no difference, no correlation, something like that, or equal to something, okay? And so if that's the case, assuming that so the data is categorical, right? Yellow, green, the different color is categorical. You have category of outcomes. So I'm going to say that, in theory, if I have a population have K category, notation-wise, I try to define the notations, I can give you the formula, right? So observed frequency for these K classes, we're going to denote this O1, O2, up to OK. O1 means the observed frequency from the first category. All right, so in this case, it is what? 56, right? Is the observed frequency for the first color. And the next one, O2 is 52, and O3 is 92. Hope that makes sense? Okay. So O denote the observed frequency. If you add them up, it will be the total sample size. So if I have 200, right, candy that I observe, the cap N will be 200. Hope that makes sense, right? And then the pi is actually the percentage distribution for each category. So we say 30, 20, 50, right? So this pi 1 would be proportion of the first category would be 0.3. Pi 2 would be proportion of second category would be 0.2. Right? So it's 0.3, 0.2, and 0.5. That's pi. That's the theoretical probability distribution, right, in the null hypothesis. And what is this E? E are the these E's are the expected frequency. So if null hypothesis is true, the distribution 30, 50, 30, 20, 50, what kind of expected frequency you will see? What frequency you expect to see from these three categories? Of course, if I have totally 200, if 30% is in this category, and I should have 60 counts, that right? 30% of the 200, right? If null hypothesis is true, you should expect 30. So E1 will be 30, E2, I'm sorry, 60, right? Because you have 30% times 200. E2 will be 40, and the E5 will be 100, right? 50% of the 200. So that's the expected frequency. Hope that makes sense? So you probably see realize that to find the E1, you just use the total count times the proportion, you get the E1, right? Total count times the proportion of the second category, you get E2, and so forth. Right? So these expected frequency are total counts times the proportion, right, for each of the category that you under the null hypothesis. Hope this makes sense. Right? So if I have this, for this data, I can compute this statistic. This is called chi-square statistic. What it does is actually you find a difference of the observed frequency and the expected frequency and square it. So what I'm trying to do is actually try to figure out a difference between these expected frequency and observed frequency. If they match pretty close, then that means my data, right, fit the data, or my model fit the data pretty well. That also means by my data follow that particular model, distribution model. Okay? So to find a difference between these two distributions, what we do is find the difference of these two and square them and keep accumulating them. Okay? And statistician realize that if you do this, find a difference between the observed and the expected, squaring it, divide by expected. Do that for all these different categories and add them together to accumulate those deviations. This quantity under null hypothesis, under the hypothesis of that particular specific distribution of the color, this statistic follows so-called a chi-square distribution with the degrees of freedom k minus 1. What is k? K is number of categories you have. So if we have 3 different colors, k will be what? 3 minus 1 will be 2. Okay? And this chi-square distribution is actually a skewed distribution. It takes on only positive number. Okay? Most of the chi-square distribution, let me quickly draw a picture. I should have. Let me show you. Oops, not so good. Anyway, so that chi-square distribution usually look like this. Chi-square, right? And start from 0, because this kind of number never be negative, right? You're accumulating square of deviation. Square of any number is positive, right? So this chi-square statistic always positive, and it's skewed to the right side, right? So this is kind of distribution chi-square has. And it also has a degrees of freedom determining what kind of shape it is. Right? When you increase the chi-square degrees of freedom, if it increases, the shape probably will go more like this and keep moving. The peak is moving towards right. Right? That's the nature of this. But I just want to tell you, this is another distribution, and its parameter is a degrees of freedom. Okay, like T distribution, its parameter is degrees of freedom. Okay, so we have a sampling distribution. So this is a sampling distribution of this test statistic chi-square. And area under that curve is the probability. Okay, now there is a large sample condition for this. This test statistic works well when the sample size is large enough. Okay, and what's a large sample condition? Now you remember when we're done with categorical data analysis for one categorical variable, bivariate categorical variable. When we do talk about proportion, estimating proportion, that's categorical variable. What's a large sample condition? We say that n times p and n times 1 minus p. Each category you expect to observe at least 5 counts, right? Some of books say 10 counts. That's fine, right? Just try to be more conservative. Okay. A lot of books say 5 counts, right? So either one, right? In our class, either one is good, right? And this is kind of extension to that. Because this time, the data is slightly different from what we had, right? We have multiple categories, right? Here is a Cochrane's guideline and about large sample condition. The guideline is none of the expected cell counts should be less than 1. Now, you don't want to see any expected cell count less than 1. Okay, those E's, you don't want to see any of those less than 1. Also, no more than 20% of expected cell frequency or less than 5. So when you calculate the expected cell frequency, some of them may be less than 5. Some of them are greater than 5. You don't want to have more than 20% of those cells, right, whose expected cell count is less than 5. So let's say if you have 10 cells, right, 10 category. If you have 2 category that have expected cell count less than 5, that's on the borderline. If you have 3, then this test will not be performed quite well. Okay? So that's the idea. And the decision rule, once you have the test statistic, then you can make the decision now. Usually, if the difference between the observed and expected frequency is too much, right, then this chi-square will be too large, right? The larger this chi-square score, the more likely you're going to say that there's strong difference, right? Significant difference between your data and the ideal distribution. So larger the chi-square statistic, the more likely you will reject the null, right? You reject the no difference except the alternative, that there's a difference. Okay, so tests like this is always a right-sided test. Okay, so when you have a chi-square statistic, usually if you do critical value approach, you will have a critical value on the right tail. So if I have 5% level of significance, you will use 5% of significance to find a critical value, right? And if you have a statistic lie to the right of it, you reject a null hypothesis. Or we emphasize the p-value, right? So if you have a chi-square statistic calculated there, then area to the right of this chi-square statistic, this will be the p-value. Okay, and there's a table for you to find the area to the right of test statistic, so you know how to draw a conclusion. Okay, so the idea is similar to the t-test or z-test, right? Except for now it's a different distribution. In this case, always the right-sided test. Hope that makes sense. Okay, and also that rule, you reject the null hypothesis if the p-value is less than alpha. Right? Like I said, always that if you use a p-value, the rejection criteria are always the same. P-value less than alpha, right? You reject null hypothesis. And the alpha level people usually use is 5%, 0.05. Okay? So hope this makes sense. Right? So let's look at that data. This is my observed frequency, 56, 52, and 92, so total is 200. To do this problem, you also need the expected frequency, right? So you use the 30% point 200, you get 60, 20% times 200, you get 40, 50% times 200, you get 100, right? So that percentage specified, you can use them to figure out expected cell count. Then what you do, find the difference of each pair, square it, divide by the expected cell count. Do that for all 3 cells. So this is easier than the formula. If you look at the formula, it's easier than those T, right? I guess. Right? Most of the students say that. And once you add these numbers up, you get the chi-square statistic 4.507. And you will look for a chi-square table to help you to see whether the evidence is extreme or not, right? Is this chi-square statistic lies in the right tail 5% of the distribution? Or is the area to the right of the statistic smaller than 5%? Right? If that's the case, your evidence is extreme, right? Or significant. If it's not, then your evidence is not significant. Okay. So let me find this chi-square table that where's my chi-square table? Okay, so let's look at this chi-square table. Where's my chi-square table? I have one on the computer, but I thought this would be more clear. Let me see. I put it in the wrong order. Chi-square. Okay, got it. And again, different book has different type of chi-square table, right? There's one table that's similar to the first table you saw, and then let me show you this one, okay? This chi-square table gives you the upper tail chi-square distribution associated with different degrees of freedom. Upper tail area is here. Okay, and number over here are the chi-square score in the chi-square distribution. So if I have a degrees of freedom, and that problem was 2, right? So your chi-square distribution is over here. These are the chi-square score with the degrees of freedom 2, and these are the corresponding tail area, right tail area. So if you have a chi-square score is 4.6, your right tail area is 0.1. Okay, that means if this number is 4.6, this tail area is 0.1. Okay? And if you keep going down, if you have 5.0 and its tail area is 0.08, and keep going, right? If you have a tail area is 7.82, its tail area is 0.02, and that's smaller than 0.05. So the larger the chi-square score goes, the smaller its tail area, of course, right? When this chi-square score moves further towards right, its tail area is getting smaller and smaller. Okay? Now, in our case, we have 4.507. If you come back to this table, the smallest we have is 4.6. And for this one, its tail area is greater than 0.1, right? So if you have a number that is 4.5, its right tail area should be bigger than 0.1. So if it's bigger than 0.1, that means bigger than 0.05. So you fail to reject the null hypothesis. Does it make sense? Right? Your chi-square score just not big enough. Okay. Now at the 5% level of significance, 5% level of significance, the score is 5.99. Okay. Now if you look at my notes here, actually I say 5.991. Right? I have a table. I use a table when I make this note. I use a table to have one more significant digit decimal place. Okay. So that's why I say I find that critical value, in fact, at 5% level. The score is 5.99. But my test statistic is 4.5, even smaller than that. So it's to the left of it, right? So its right area should be small, it should be higher than 0.05. Hope that makes sense? Okay. So this tells us I'm not going to reject the null hypothesis. That means the evidence kind of support the alternative. I mean, it doesn't support the alternative, that there's a change in color distribution. Okay. This is based on a sample of 200. If I have a sample of 2,000, it may be different, right? If I have the same data, but same proportion of color distribution from my observed frequency, if I increase the sample size, it may change. Because when you increase the sample size and increase the sensitivity for the test to detect difference, that's the same for all the tests, okay? But when do we use these tests? Again, hypothesis testing. Usually we use that for sample data that is not large. Right? You don't have millions of candies for you to check the distribution. You only allow to have like at a time to check 1,000 or check 500. Then you use them to do hypothesis testing to do it. Right? If you do have millions of candies that you can count, of course, then you will use the descriptive statistic. That's good enough to show us whether the distribution matching the 20, 30, 20, and 50% or not. Am I making sense? Right? When you have large data, oftentimes descriptive statistics themselves are useful, right? Good enough. But if you have small data, not so large, medium size or smaller data, this is where these statistical inference procedure becomes more useful and important. Okay? And oftentimes it happens, right? In a lot of scientific research, you can get large data. Not like the data you can get from internet, right? Data you can get from internet, you can get millions, billions of data every day, right? Then it requires other kind of data analysis technique. Some people call them data mining technique or large data, right? Analysis technique. They're People use visualization. People use all kinds of algorithm, right, to find information from there. Right? So that would be slightly different from what we learned here. Right? What we learned here, the second part of this course is about statistical inference. Right? That's using these probability model based on the data to infer what's happening in the population. Right? Large data will be slightly different. Although when people deal with large data, sometimes they also come to the statistical inference procedure to help them for decision making. Okay, just like you to know, right? Maybe in the future, some of you probably will be doing a lot of data analysis, right? So actually, it's fun, right? Doing data analysis, it's fun. Okay, so that would be your conclusion. Again, when you do a problem like this, I'd also like you to draw a conclusion about the alternative, right? If you don't reject null hypothesis, what does it mean? In this case, you don't have evidence to support that there's a difference, right? The distribution is different from 30, 20, 50. Okay? Make sense? And this is not hard, right? This kind of problem, I think most of the students say they're simple. They're not as hard. Do you want to try one? This one? See if you can do it. This one actually, what is it? We have 4 different balls. Each ball has a number label on it. This could be setting up a lottery game, right? And you have 4 balls, you're going to do random draw, and you want to design a fair game. So if it's fair game, then each ball should have the same chance to be selected. Okay, something like that. So the game designer actually get these 4 balls, and they want to see whether these 4 balls distribution outcome, right, or distribution are the same when you talk about drawing a ball from these 4. So 100 game or 100 drawing, right, would perform. Each time you just draw a ball from these 4 numbers. So out of 100 trials, 20 times turn out to be number 1. 25 times turn out to be number 2. And 41 times you get 3, and 14 times turn out to be 4. Does it suggest that we have a uniform distribution, right? That all numbers are equally likely to occur? Okay, so for doing this, of course, the first step is stating your hypothesis, your null and alternative. And what's a null? Null will be distribution for all numbers are equally likely. Now, when you write a hypothesis, even for the exam, right? Null hypothesis, if you like to say mu equal to 0 or proportion equal to each other using math notation, that's fine. If you like to write a brief description, say null hypothesis, all colors are equally distributed, right? That's fine. Okay, and over here, if you want to write it a mathematical notation, right, then you can say that P1 equal to P2 equal to P3, how many? P4. Proportion of all these 4 colors, numbers are the same. Okay. In the alternative, you can say P1 not Pi not equal to Pj for any pair of ij. Right? So it's any pairs, right? There's a difference, right? As long as one pair difference is significant, that means the distribution is not uniform, right? For maybe better say for at least one pair, right? For at least one pair, okay? For at least one pair. Pi not equal to Pj for at least one of those Pi, Pj, okay? It could be all of them are different. It could be just first one different from the third one, whatever, okay? Or you can simply just write on the phrase, say, all proportions are equal, and alternative is at least one pair, right, of category, the proportions are different. Right? That's good, right, if you like to do it that way. Okay? And the next thing you would do is what? Following this example. Next thing you would do, that's what I would recommend you to do. Make a table like this. List all the observed frequency you got there, okay? Find out the total, and then calculate all the expected frequency if they are uniform. if they're uniform, then each number should have 25% chance, right? Out of the 100, right? Was that 100? If there were 100, then each category you expect to see 25 counts. Right? So with that, you can actually calculate a chi-square test statistic, right? So first fill in these numbers. What are the numbers? Let's go down to there. The numbers were 20, 25, 41, and 14. And so it should total up to actually 100, right? Okay, so write these 4 numbers down. And that's these 4 number. Actually, there should be 4 number, and then plus the total. Total should be 100. Then you use that 100, multiply the proportion for each of those numbers to occur if it's uniform. Out of 100%, if each number have the same chance to occur, then each number should have 25%, right? So 25% of that 100 should be for 1, 25% for the 100 should be for 2, and so forth. So you have a row of 25, in fact, right? Then what you do next is calculate this chi-square statistic. It should be what? Your first number minus the expected 25 squared divided by 25. And second number minus 25 squared and divided by expected 25, and so forth. That's what you would do. While you were doing this, you should be able to check the large sample condition. Are any of these less than 1? No. Do I have 25%, more than 25% of 20% of a cell count, expected cell count less than 5? No. They're all greater than 5. So large sample condition satisfied. Okay? Make sense? Now, if large sample condition is not satisfied, then there are other tests. We're not covering here, but there are tests for it too. And some of the software will also give you that even you have small sample, they automatically switch to a large sample procedure and report to your p-value. Right? Anybody got the answer? Is it uniform? Does this data support that numbers are uniformly distributed? Oh, by the way, I don't know whether you have a chi-square table or not, right? This is a chi-square table if you don't have a chi-square table. Okay, chi-square table. This one, degrees of freedom is what? What's the degrees of freedom for this? We have 4 categories. Our degrees of freedom is number of category minus 1, right? So that's this. So this is that chi-square distribution you will use. And if you have a score that is in this range, you'll be able to figure out the p-value. It's right tail area, right? If your score is not among them, then you're going to say the p-value is higher than 0.1. Okay. So do you have p-value higher than 0.1? How many of you have rejected the null hypothesis? Oh, okay, so that's cool, right? So let's see. This is what you would do. You find those expected count, right? And then they're all 25, right? And the observed count is 20, and then what? 25, and 41, and 14, right? These are the observed. Observed minus expected squared divided by expected. Observed minus expected squared divided, and so forth, right? So what number do you have? Anybody? 16.08. That's pretty large, all right? 16.08, if you come to the table, 16.08 is in between these two numbers, okay? So you know that a p-value should be less than 0.05 for sure. Okay? It is in between these two numbers. So its p-value is between 0.05 and 0.05 and 0.01. So you can say, if you use a table like that, you can say p-value is between 0.001 and 0.005 from the table. And that helps us understand whether the p-value is less than 0.05 or not, right? 0.05 is a cutoff, right? So this is less than 0.05. The p-value is less than 0.05, so I'm going to reject the null hypothesis. And again, your conclusion says, since I reject the null hypothesis, 5% level of significance, I'm going to conclude that my evidence support the alternative that numbers are not uniformly distributed. The outcomes are for different numbers. They're not uniformly distributed. Okay. So you got to do something about those balls because you have an unfair game, right? In fact, if you play the game, you probably will bet on numbers 3 more often, right? You have higher chance to win. And you calculate. If you use these numbers to calculate, well, you find a relative frequency, use these numbers to figure out the expected value, you will know, right? How profitable it'll be, right? If you keep betting on that, right? Okay, makes sense? So that's a goodness of fit test. That's a simple test, very simple, I think. Most of the students like it. Okay, so that's actually when you're dealing with one variable. So in fact, if I have this problem, I only have 2 categories. The problem reduces to testing for proportion. Does it make sense? Okay? So this is kind of extension for that proportion, test for proportion. Extend to having multiple categories. Hope you see that. Okay. And in fact, there is this relation between the chi-square distribution and standard normal distribution. When we test for proportion, the test statistic is z, right? Z is standard normal. Chi-square actually is square of z. Right? You square in z's, right? It becomes chi-square. Okay, it depends on